Okay, so I'm going to present an overview of the lake applications, what we have been doing with coherence in SYKE. So I work at the Freshwater Center, and also we do some river modeling, but we use different software for that. So this is about the lake models. I will first tell you a little bit about the challenges that come with shallow water modeling, and then I will show most of the applications that we have done in kind of a summary way, and I also have a few examples. So Timo has already told something about this, but coherence has been used about 10 years in SYKE. So from 2006 to 2011, we used coherence V1, and after that we have migrated a little bit to the V2 versions. We use many different V2 versions. We've done freshwater, coastal and marine applications on many scales, and most of them are full 3D models. We've made a few 2D models and maybe some tests with the 1D mode, but mostly are full 3D. So currently we have applied coherence on over 13 freshwater sites. Several more are on the way, and we are currently working on them. And also the same model on the same site has been used for several different projects or applications. In addition to these freshwater sites, there are approximately 5 coastal or Baltic Sea models with salinity included. There's 2 or 3 persons working with freshwater models currently, not always full-time, but still every now and then, and 1 to 2 with marine models. And our models are mostly research models, meaning that we don't run forecasts with them operationally or automatically. We do the kind of boundary conditions and forcing manually. So some of the challenges of freshwater modeling in Finland. Well, one of the first thing is, of course, what to model, because we have so many lakes. So 309 lakes of over 10 square kilometers, and almost 200,000 lakes of over 500 square meters. So there's quite a lot to choose from. And this means that the same model is rarely used twice. So we must start to set up calibration, validation from scratch in many cases. There's also no typical lake from 3D modeling viewpoint, because all of them are a little bit different. Some might be more varied in bathymetry, and some are more shallow than others, and so on. So good workflow practices are important. So we need to know what we are doing when we start a new project, and in where we get the data, how we implement it, because limited time is for each project. And also the data is of course limited, because all of these resources have to be divided on many different lakes. Of course we don't have data on nearly all of those lakes, but even the few that we have data from, there's not too much always of it. Also the waterways are very complex, and also the seasons make their own problems. Winter, shallow and complex bathymetry, shorelines are broken, the terrain is varied, and there are lots of trees. It causes wind shading effects to the modeling. And especially the winter time, the ice cover changes the surface fluxes quite dramatically. So it essentially cuts them off and reduces them to almost zero. Also because of this, the boundary effects are so great that many phenomena that are not important really on marine models become important on lake models. And this also means that we need very fine time steps to resolve the issues. As you can see from the picture, this is Repovesi, and this is just an example. We also have some, of course, lakes that are more open, but we often have to model lakes which have these kinds of narrow straits in them. So what we usually do with lake model, we take the marine model coherence, and these are usual changes that we make. We make some optical module changes, especially with the parameterizations, to change them to fit the shallow areas. Then we use an ice model, which is actually copied from this MyLake model, which is called Saloranta model. It's 1D and it works very well. It's a thermodynamical model and it works extremely well. We just put this 1D model on each of the 3D grid points and let it run its course. Then we use bottom heating, or actually more generally it's a sediment heat exchange, but in the winter time we can approximate that it's something like 5 to 10 watts per square meter that is coming to the water column from the bottom. And also we need to take into account that evaporation and precipitation changes the water level quite dramatically in lakes, so we actually have to explicitly take that into account. So this is a short code kind of showing how we use this evaporation precipitation fix in coherence, but it's just very simple, and it can be improved too, but we usually use this kind of code. Yeah, and this is kind of what happens with if we don't take that into account. So this blue line is the water level, and these are the observations. This is the kind of if we don't account for the evaporation and precipitation affecting the water level, this happens with the model through the summer. And if we take that into account, we are kind of at the mass balance of the water stays quite close to the actual measurements. This is an uncalibrated model, but the mass balances are very important in lakes. So we have 3 types of lake applications basically. So one is the physical model. We only use currents, elevation and temperature. Then our so-called basic product is the transport model, where we have this physical model, and then we transport some substances with it. It might be wastewater or chemicals. And then we have this water quality model, which includes all of these in addition to some process models. And I tried to make a map where there are all the different lake models that we have done with coherence here in Finland over the years. There are a few green ones, pointers, which actually are lakes that are less than 10 square kilometers in size. The blue ones are kind of normal lakes which are over 10 square kilometers, and the yellow ones are places where we have not yet had a model, but we are going to do them. It's certain now. So this is one example, Lake Pyhäjärvi, as Idrissa was showing. This is the same site. We have a model for that. This is the easiest lake for us, really, because it has 1 or 2 islands, and it's very open and it's nicely shaped and so on. There's not too much trouble with that. Then here I work in the SYKE's Jyväskylä's office. We have 3 small lakes there: Lake Palokkajärvi, Lake Tuomiojärvi, and Lake Jyväsjärvi. These are very small and shallow lakes. These represent the kind of at the end of the spectrum where we go to the very small lakes. And then there's this Lake Piensaimaa in the eastern part of Finland, which it's kind of very, very broken place. Even though it's quite big, it's very broken and has lots of straits that are difficult to model. And also here is in the kind of a table format of all the places that we have modeled. I'm not going to go through all of them. It just shows something like this is the smallest one what we have done with Coherence Lake Pyykkösjärvi near Oulu, which is only 1.5 square kilometers. And going up from that, it's Lake Jyväsjärvi and so on. And we have done kind of many different model developments with all of these different lakes, because we always try to do some model development every time we model some new place also. So as you can see, there's lots of there's ice model development and spreading evolution of organic thin compounds and things like that. And then there's another page of these. The largest one is actually Southern Saimaa, which is only a very small part of the whole lake system, which is Saimaa. This is 600 square kilometers, and this was actually for Coherence V2 tests and some contaminant transport studies. Okay, then some examples of certain lakes. This is Lake Onkivesi. This model has actually been done with Coherence V1 a couple of years ago. It studies the transport and mixing of wastewater effluent, and the lake system is pretty complex, and we compare the different discharge sites to give information to decision makers. It's located here, north of Kuopio. This is zoomed in a little bit. This is the whole model area. It's about 10 by 30 kilometers. And this is the area that we are really interested in the model. The water flows in from the north through these channels, and there's different discharge sites for the wastewater here. So these are some of the results. I think in Timo's presentation you saw these pictures already. We did some steady state scenarios and some dynamic scenarios with the real forcing, and also had some particle and concentration tracers and compared 5 optional discharge sites. So this is the current situation as it stands. The discharge site is about here, and then there's different options. And here's one of the options, or I think this might be the original one, just showing you how nicely the coherence resolves this issue, and to give you an idea of how complex this system is, because the water currents are constantly changing direction and moving in these narrow straits to different locations. We managed to actually calibrate and validate this model quite well. And up here, it's just the colors are the concentration. So this is 0 concentration, this is 1, so it's the maximum concentration. Actually, the units doesn't matter in this test. Now, the wind direction is also up here, if you see that. Okay, moving on. Then there's this Lake Pien-Saimaa, which is a quite complex system. We made this water quality model there and studied what this accelerated water exchange means. I will show you that. So the natural water exchange between this Saimaa proper is through these broken areas here. Otherwise, there are many areas that are quite isolated from all the water exchange.
And let me just make one advertisement. Our university is right there.
Yeah, yeah, that's correct. Yeah. Then there's, since I think almost 80 years, this kind of pumping station has been here that is pumping fresh water from Saimaa into Pien-Saimaa, and to make the water quality better, because the water quality there has been a problem for a very long time. So we have made this coherence model, and this is the bathymetry, and to study how to make the water quality in these southern areas even better. So the idea is that we would add another pumping station here and see how these southern areas get the fresh water and better water quality. So this is done with edge tracers. So here is the scale. If it's close to zero, it's fresh water and good water quality. If it's very red, it's old water and bad water quality. So this is the current situation here. There were many different options, and as you can see, this southern side is very bad. This is actually the interesting place because they have now put the pumping stations here in this place. And this is last winter when they were installing it. And as you can see with this pumping station, the modeling results show that the water quality will be much improved compared to this one in here. And the initial results show from this autumn that indeed the water quality has increased a lot because they have been now using the pump for under a year. But it kind of looks like that the model is validated in reality too.
Also, by the pump was designed by the university staff, and it's a bio-project engineering.
Yeah. Very shortly, this is something that we are doing right now. This is Coherence V2. We are doing this nested model in very high resolution of this Lake Keurusselkä near Jyväskylä. And the inner grid will be around this area. It will be very fine, maybe 10 meters or 5 meters or something like that. But we haven't decided on the real grid size yet. But the idea is to study this water and sediment contact time. Okay, so what we are going to develop regarding lake coherence modeling, we are going to migrate to the latest code because there are many improvements that we like to use. Then there's many developments that we have done for example, this ice model, sediment heat exchange, and so on, so that we can solve some of the shallow water heat balance issues that are coming from the boundary condition or kind of this boundary effect area. We want to also kind of implement methods to produce local wind fields because the atmospheric forcing is very important because the lakes are always driven by the wind. Also, as we are doing so many different lakes, we need tools and methods to accelerate this model development. We can't use 2 years to make one model. We might have 2 months to make one model. So it won't be perfect, but it needs to be good enough. Okay, conclusions. The model processes are a little bit different for these shallow lakes here in the very north compared to marine models, and we need to change the parameterizations and maybe write our own process models for some of them. We've used the coherence successfully on quite a variety of different kinds of lakes. And in general, the model behaves quite well, but as I said, some of issues are still with the heat balance, but we are kind of coming to a solution. We know what to do, but we just need to implement the fixes. And we also now have a kind of a very reasonable starting point to model different types of lakes because we have done over 13 lakes already and of very different types, so we know what are the issues in very broken lakes or very small lakes and so on. And we know how to go on from there. That's it.